Even though I am the presenter of the paper, as you can see in the bottom, I am not one of the authors. My colleagues at Amazon asked me to present the paper on their behalf, and I'm doing so, but I had nothing to do with the paper, so I'm going to do my best. All right, so as you can see from the title, the paper revolves around reinforcement learning. And so I'm going to first start with a very quick recap of what reinforcement learning is and why it is useful for our community. Then I'll give some background specifically about the problem that this paper tries to solve with reinforcement learning on a offline to online setting. And then we're going to present the meat of the paper, which is the WSMAC algorithm. It's a realization of some very simple idea that actually improves the offline to online transition of reinforcement learning. And then I'll show you a number of slides with results of different kind. And then we're going to just conclude with future work and discussion. Okay, so let's start very simply with why reinforcement learning. This would be no surprise to this community. We've been trying to do building controls for a while, and one of the most effective ways of doing this to avoid having to model the building is to use model-free reinforcement learning. It's a much more adaptable and much more scalable solution because we don't have to spend much energy or cost in creating models in simulators. And the way that this works is you have an agent that builds a world model and more specifically learns how to control by interacting with the environment. So the environment is represented as states of the environment, actions that you can take on this environment, and the rewards that you get back from doing so. And the agent, by interacting with this, just learns a policy that allows it to control the environment much more efficiently. That's a general overview. Typically, this is posed as a markup decision process, is a sequential decision-making problem, and there are formal ways to describe it, but I'm not going to go into the details of that, just to give you an overview of where we are. Okay, so if you know about reinforcement learning, you may also know that there are many approaches for reinforcement learning. Even if we're just taking the model-free approach, you can use a model-free approach in an online setting, in an offline setting, or as this paper does, in an offline to online setting. Each one has its pros and cons. As you go to the far right, you get better aspects of applying reinforcement learning because you don't have to have models beforehand. You don't have to rely on an actual simulator. And so it is very beneficial to go in a offline setting and just learn from existing experience that you get from building automation system data, for example. However, when you look at the literature of online to online RL methods, there are requirements that they have that are not necessarily met today. One of the requirements is that you need to know how random policies or random agents compare to experts that are trying to control the building. And you have to have scores for both in an absolute way, not just relative. And these are typically not available. You just have actual experience from a controller that has been in the building in the past. And that controller is usually the expert controller. And you don't have data from random exploration of what happened before. That's one requirement that isn't met. Second requirement is that many of the policies, once you try to optimize them in an offline setting and bring them in an online setting, meaning you try to interact with the building after you've only learned from replay data, they collapse because in the replay buffer, they haven't seen enough of the distribution of states and actions to know what to expect when things change. Then the last one is that all of these require much more compute because you may have to add additional models to figure out all the replay settings that could happen. So we want to avoid the additional compute. Those are the three requirements that this paper tries to overcome. And just as background of where these experiments are going to be run in the paper, there is a single building simulated in Energy Plus. It's a single story building with 5 zones. where the state that they're modeling includes temperature, humidity, wind speed, and direction, 20-dimensional state. And the actions are the heating set point and the cooling set point for the interior zones. And the reward is basically the energy consumption and the absolute difference to temperature comfort. It's a combination of both. And then the episodes are a full year of 15-minute time steps. Yeah. So the way that the offline to online setting works is you start with a replay buffer, which is D, which consists of a set of tuples that have the state, the action, the next state, and the reward that you obtain from, again, maybe building automation system data. And then from that data, you can pre-train an offline model that includes a policy and a value function. And then you feed that to an agent that starts interacting with the environment using that policy. That leads to new state transitions, and those are then stored back in the database. And at that point, then, having seen what happens in the online setting versus the offline setting, you can fine tune. So you can update the policy and you can update the Q values. And then continue to do this over and over. Right? So the red line here is what happens in the online setting. Just for the record, online here doesn't mean that it is online. It basically means that it is doing so in an actual building, not with offline data, not with data that was recorded ahead of time. Right, so again, this is the general offline to online setting. It has the same requirements that I talked about before. What is the innovation in this paper? Well, that's WSMAC, the weighted increased simple moving average of Q values. And it's a way to adapt to distribution shift. Once you go from the offline to the online setting, the distribution of your state action pairs changes and your value function changes. So how do you adapt to that smartly? And so it is based on a simple realization. And I'm going to try to do this slightly more interactively. Say that I don't know how many people are paying attention, so we're going to give it a try. Say that I were to ask you what you expect would happen if I take a policy that was trained offline using an expert, which was, let's say, a rule-based controller, and then I try to improve upon the rule-based controller, and I plot over time in my online setting, what is the mean value of the Q function, the value function? Like, do you think that that's going to go up, meaning it's improving its performance over time, or do you think that that's going to go down in the online setting? So I trained it on an expert. Let's say I have a rule-based system in my building, and then after I've acquired data from that rule-based setting, like exactly what it did on every one of the state action pairs, I pre-trained my algorithm, and then I deploy it on the actual building. What do you think will happen? Will the online setting continue to improve, or will it struggle to improve over what the rule-based algorithm was doing? Okay. Hard question. The answer is, in the rule-based control setting, the Q value is decreasing. That's because it's kind of hard for this algorithm to optimize above what the rule-based controller was doing. And so what we have plotted here is time steps on the bottom axis, the mean Q value in the y-axis. Then the blue dark line is the average Q value over the sample batch. Remember that this is like many, many replays, right? So the average Q value over the sample batch, and in the light blue, we have the mean and max value over that sample batch. And as you can see, this is going down, so it's not actually improving. But if we were to choose a pre-trained model on a completely random controller, so it wasn't like a rule-based controller, it's just random, then our Q values are going to improve, right? So with this realization, that's the first realization, and the second one, which is, because this is very stochastic, maybe we just want to do a moving average, which is the red line that's here. That's a much more smooth indication of where we're going. Are we going down or are we going up? And then with that, I can regularize how much I trust the indications of this to be fine-tuning my policy or not, right? So should I not fine-tune or should I fine-tune depending on this? So that's the conceptual innovation. To put it in math, what ends up happening is that on updating your policy, in addition to the first two terms here of this expectation, which are the update of the Q value and the behavioral cloning, which happens on the second one, we add this third term, the WSMAC penalty or the WSMAC loss, which is basically just a value that is between 0 and 1. That's what the ReLU function does here. And it is 0 when these things are not improving. So it goes back to like, I'm just going to do behavior cloning. I'm not going to be trying to improve on these new samples that I have here. Okay? That's essentially what it does. Having introduced the mathematical form and what the innovation is, let me go into experiments. So very quickly, we have 4 sets of experiments: the benchmark, the data efficiency, the sensitivity, and the scalability. All right, so first for the benchmark, what you have to be paying attention to here is the results of the red line, which are WSMAC. We have time steps again, but instead of now plotting the Q value, what I'm plotting is the normalized episodic reward. So for every reward, for every episode, the reward should be between 0 and 100. 100 is the expert reward normalized, and 0 is the random reward normalized. So if it gets to 100, it's close to expert. If it's close to 0, it's close to random. And the red lines over here, compared to the other algorithms that exist, is actually doing much better. This is the same thing in tabular form with numbers here. And because there's variation, because of the stochastic nature of the replay buffer, that's why we have confidence intervals in each one of these. Right, so WSMAC is doing better than the others. If you consider how much data you have, then there's something else at play here. So you could have the replay buffer be just 1 week. Remember that we have an episode of 1 year, but we could say like it's just 1 week. And every time we get a new day, we just add it to the replay buffer, forget the last day, and then just keep going. It's 1 week always. If you do that, that is what the red line does. Kind of does well, but it's very stochastic. It can change a lot. And if you put the full year, which is what you have on the blue, then it will consider things that are very old and not be as quick to change when new settings arrive. So it's more slowly moving with a lot more variation. That's the data efficiency experiment. They recommend that you pick somewhere between the 1 week and the 4 months, and not the full year. Then there's also sensitivity. You remember that we had a psi value next to the WSMAC loss in the optimization in the way that we update the policy. If you pick that value, the hyperparameter psi, to be very low, like 1, then essentially your normalized episodic reward will not work very well. It will just start decreasing. But if you put it very high, then it may overcommit to how well the Q value is working. So again, they recommend somewhere between a very high value and a 7 or whatever value you want in between there, because that allows for a lot more adaptability. But don't put it very low. The other 2 experiments are the scalability and the ablation. So on the scalability front, if we move this to a different setting that is not the 5-room Energy Plus model that we had there, but put it on a data center, we can still see that other models struggle to adapt, but WSMAC does very well on a different setting right from the get-go. And on the ablation studies, it's not clear what part of the WSMAC and the whole algorithm is actually doing better. So it's they tried some experiments where they removed components of the WSMAC framework to see which one was actually leading to an increased reward. So if you remove WSMAC entirely, that's the green line. If you just remove the fact that it is using the replay buffer on every batch and continue to update there, which is the CER, then it does a slightly better. And then when you use WSMAC, you're actually improving all the way. That is the end of the experiments. And then the last slide that I have is on future work and discussions. The WSMAC algorithm presented here, as shown, was able to adaptively regularize the policy. It requires no change in the offline model or pre-training, and it just has better computational efficiency because it's just a simple moving average. It outperforms the other models that we had there by 32 or 33% on average, and all of the source code for this is available online over here. I'm at the 15-minute mark, and thank you. I can hallucinate answers for you on the spot, like a good LLM. Questions?
A lot for the great presentation, Mark. I'm Yufei from.
I can't hear you. I don't know if the microphone is on.
We.
Oh, yeah, now it's good.
Yeah. Oh, thanks for the great presentation, Mario. My name is Yufei from EPFL.
Yeah.
So I think like it might be a bit practical question that it recalls me some experience when we need to implement this like intelligent building controller. Might have to reason to the building manager that somehow how this action or strategy is generated, or try to alleviate their concern on if it's too loud or harming their comfort or machines. I was wondering, I can't fully understand the Wismo yet, I guess, but it seems like the buffer of the rule-based controller seems a promising way to somehow address this, but look forward to your detailed explanation if it works.
Thank you. So if I understand the question, you're asking, basically from your experience, it's hard to convince facility managers to adopt data-driven controls like this in practice. And so what recommendations do I have about it? I'm not going to answer based on the paper. I'm going to answer based on my own experience. I think that there are two things that I've noticed are effective. One is instead of using model-free solutions like the ones presented here, if you use model-based solutions that actually have engineered models inside, those are much more transparent and much more interpretable, and you can sort of look at what the decision was and then trace it back to why the decision was made, and that gives comfort to facility managers. The second one is a much more practical one. You might want to engage with them in a very slow dance of letting them or having them let you control small parts, and then you proving that it actually works, and then you keep on expanding over and over. It's sort of like, yes, this is magic, but I can show you that it works. And if you see it by your own eyes, then maybe you'll trust me. Those are the, I mean, they're not very technical solutions, but those are the solutions that I've seen that actually work. Okay.
We can move.
Thank you.